Yeah, then we also have to talk about recurrent concepts in noise. So there is pioneering work back in the last century, which is called FLORA, the FLORA system, which has several levels. The most important levels are FLORA 3 and FLORA 4. And this FLORA system maintains a decision list per class. So, and FLORA 3 can deal with recurring contexts, which is probably interesting if we have recurring concepts. Yeah? So if the current concept is stable, it is stored for later reuse. So stable means it has a good accuracy or whatever. And if a drift is suspected, yeah, we inspect the concept we have stored, we have considered to be stable. We find the best candidate concept, again using accuracy or F1 measure or whatever. Then we use that to refit this concept. So reset counters and reprocess all examples in the window. We evaluate this new refitted concept. Yeah, choose the candidate if the resulting description is smaller. Yeah. So in that case, old concepts are not just retrieved, stored and so on, and also used as the current concept, but they are somehow retrained, regeneralized with examples of the current window. Yeah, because we always try to find the best concept, which can be an very old concept, and then we try to refit the concept. For example, refitting the model parameters and stuff like that. Yeah? So this is FLORA 3, and FLORA 4 adds robustness against noise. So in that case, decision lists are just allowed to cover some positive or negative examples. So basically they allow to have training error, more training error, because noise typically is responsible for training errors. So in FLORA 4, the system also allows for more training error in order to be more robust against noisy training data. That's what they claim actually. Yeah, and then there are different types of changes again in terms of speed and reoccurrence. Yeah, not in terms of what actually happens in the data, but what happens with the data. So we talked about sudden and gradual, so shift and drift of concepts. Yeah, so this is a sudden concept shift, and this is a gradual concept drift. So this is a sudden shift from blue to orange all of a sudden, and this is a gradual concept drift from blue slowly to orange. Yeah? So the change from blue to orange is sudden and gradual. That's the difference here. Yeah? And reoccurrence means we have no reoccurrence of drift or shift. Yeah, in that case, it's shifting from blue to orange, and that's it. So before we had before the shift, we had blue. After the shift, you have orange. No other things. Yeah, and here we have a reoccurrence, occurring or recurring shift or drift. Shift in that case. So from blue to orange, back to blue. Yeah, so in that case, the concept drift, concept shift is recurring. Yeah, and the work here from Buffet et al. Also suggests different techniques to be used best for different types of those changes here regarding speed and reoccurrence. So and they distinguish between single classifiers to be used or ensemble classifiers to be used. For example, in this training from junk approach using ensembles. So in that case, if you have gradual drift, then you should use dynamic ensembles. If you have reoccurring drifts, you should work with dynamic integration and meta learning. And with the single classifier, fixed windows and instant weighting is good for sudden drifts, especially if you have or think it is important to adapt to the changes. And if you want to also detect the changes, then you should use detectors and variable windows. Yeah, so this is just a kind of overview and a kind of cookbook what can be used if you want to deal with concept drift of different speeds, different reoccurrence schemes and stuff like that. Yeah, and last but not least here in this introduction, a first very simple but in some sense real stream classifier. So if we have a look at the batch classifiers we got to know, probably the lazy learners, so classifiers that do not really train a model, for example nearest neighbor classifiers, they do not train a model, they just classify based on nearest neighbors. Yeah, they are good candidates for the direct application on streams. The only problem is, upon arrival of a new object xy from the stream, we have to compute the k nearest neighbor, or the nearest neighbor, the k nearest neighbor, depending on k, of xy on the entire history of the stream. And that can be, of course, very expensive, and that is contradictory to our one-shot not accessing the whole history of the stream, the whole data, training data. So there is a proposal to adopt the nearest neighbor method to streams, the so-called dynamic nearest neighbor method, which somehow uses the idea which we had in clustering with these summarizations. So we maintain a fixed number of weighted representatives as training data, which is kind of summary information. So we use summary structures, and those are the weighted representations as training data. And we use a weighted k and n classifier on these representatives. And the online maintenance of these summaries, these n representatives, is as follows. So x, y is the observation that arrives from the stream. We determine the closest representative. If the distance of the arriving observation to the representative is smaller than a threshold tau, we add x to R. So this sounds very familiar to this leader and stuff like that. Yeah. So if the labels, so now we also have labels. Yeah. So R represents observations that may have different labels, and we count the numbers of labels, so to say, for all classes. Yeah. And the majority class. So if we have two classes, and R represents 5 positive and 10 negative examples, the count of R is 5, yeah, because it represents 5 more examples from the one class compared to the other class. So if the label of x, y, and R is equal or are equal, then we increase the weight of the representative by 1, else we decrease, which makes sense. Yeah. So if R represents, as I said before, 5 positive, 10 negative, R has the label negative with a weight of 5. And if xy, which is coming in, is also negative, this weight increases by 1, so it's getting 6, because we have now 11 negative and 5 positive. On the other hand, if xy is positive, we have 6 by 10, so the weight of R will decrease by 1, so it's going to be 4 then. Yeah. Well, if the resulting weight is 0, we replace R by this new observation. So the new observation gets or becomes gets the new representative. Yeah. And if x does not fit to any of the concepts, we add x to the set of representatives. Then we have to subtract 1 from the weights of all representatives which are not xy, and delete the least weighted R, the least weighted representative, because by simply adding xy as a new representative, the number we want to keep is exceeded, so we need to get rid of 1, and in that case we subtract 1 from all the weights of all representatives and delete that one that has the least weight. Yeah. So yeah, that's basically the idea, and that is, as I said before, the first very simple but real stream classifier, very similar to LIDA, the clustering algorithm, but the only difference basically is that we will maintain the weighting according to the class labels. That's basically it.